So what you will get is 1 plus, and now the definition for the return, that's S1 divided by S0 minus 1. Now we do the same for the second return, 1 plus the second return. Second return is S2 divided by S1 minus 1 and minus 1. Now you will see that the plus 1 minus 1 basically cancels out. And what we have left with, what we're left with is S1 divided by S0 multiplied S2 divided by S1 minus 1. And now you see that the S1 appears in the numerator and the denominator, so it cancels out. And we're left with the standard definition for the 2-year return, which is S2 divided by S0 minus 1. Right. So that's kind of a mini proof that this is actually the correct formula that I've shown. Okay. So that's what we call multiplicative compounding. So far so good. That's kind of the standard way how you probably have seen this in your introductory courses in the bachelor programs and so on. Now let's think about the logarithmic returns. Yeah. Just in terms of notation, so sometimes to make apparent that we use the log return, I put this little hat on top of the variable. So very few formulas are only applicable for these log returns. Now, the slide already gives it away. The compounding works differently, and it works additively. So our 2-year return, and this is not really simple, is just the first return plus the second return. It's R1 plus R2. So you see suddenly this has a big advantage of using this return. So if you want to aggregate them, you just have to add them up, right? So what is, in our example, then the 2-year return? Well, that's 10% plus minus 10%. And that's equal to 0. So the logarithmic return over 2 years is exactly equal to 0. So this is another reason why researchers like to use this definition of returns. For most of the time we measure returns on a daily basis, but then we're working with returns expressed as per year, right? So if you want to compute a return then of a month, for example, you just have to add up the 20 or 22 daily returns. And if you want to then add it up to a year, you just have to add up the 12 monthly returns that you're done. Okay? It's much simpler than just doing this here, 1 plus the first return multiplied with 1 plus the second, and so on. It's just tedious and much easier to do. And much quicker computationally. Okay, so the proof for this here is not really rocket science. It just requires the knowledge of one computational rule with logarithms, so it's a good opportunity to review that. So again, let's plug in the definitions from the previous page. So the first return is the natural logarithm of S1 divided by S0. And the second return is the natural logarithm of S2 divided by S1. Now comes the thing that we have to know about logarithms. So someone know how we can split up this first term here? Can I kind of rewrite the logarithm of a fraction?
Difference, logarithm of S1 minus logarithm of S0.
Yes, very good. It's the difference of the two logarithms. So this is the logarithm of S1 minus the logarithm of S0. Now we can do the same with the second part, which is the logarithm of S2 minus the logarithm of S1. if you look at the resulting formula, you see that we have plus the logarithm of S1 and minus logarithm of S1, so these two terms disappear. So this cancels out and this cancels out, same as these here. And now we just basically do the reverse, right? So we have logarithm of S2 minus logarithm of S0. Now we apply the same rule in the reverse, and then we're already done. So this gives us then the logarithm of S2 divided by S0. And this is exactly the 2-year return if you just apply the formula from the previous page on just the first and the last year. Maybe just out of curiosity, who of you have already worked with logarithmic returns before, or is this kind of brand new to most of you? Who didn't know about this before? No one. Okay. Right. So I think I have somewhere an exercise, a problem set where kind of just a bunch of returns that you have where you can aggregate them, average them. That's maybe a nice exercise to start off with. And we're actually working with some real data later on, and we can also basically do computations in both ways in Excel, such that you get familiar a little bit with it. Right. But just to kind of assure you, this is kind of the level of logarithmic calculations that we're going to do. It's like not getting any more fancy than that. So what we've computed here are now 2-year returns, right? It's a return from time 0 till time 2. Again, you can express returns over any time period that you want, but it's standard in, for example, research literature to annualize them. Annualize means that you now express them as an average per year. Right? So the question is, how can we make an annual average out of these 2-year returns? And that's here on the next page. So the idea is now to compute the annual average return over the 2 years. And again, I've already told you what the rules are to apply here. Again, we have different methods. The way how we average over the discrete return is using the so-called geometric average. And for the logarithmic return, we're using the arithmetic average. Let's start off with the geometric average. So in this case here, that will be, well, there are 2 ways now of writing this down. So what you could do is you could, if you want to use the single year returns, you could use 1 plus R1 multiplied with 1 plus R2. And now you have to take the square root out of this and subtract minus 1 at the end. Alternatively, we have already basically shown that this here in parentheses, this is what's kind of behind, below the square root, that is 1 plus R0, comma 2 from the previous page. Right, that's the same thing. So you can either use the annual return, so that 1 plus 10% multiplied with 1 minus 10%, then take the square root and minus 1. Well, basically, you take the root of the number of years that you have. If you have 3 years, you have to take the third root and so on. So maybe I'll put this down here explicitly. So that's the way how this is done here, and I'll maybe plug in the numbers quickly to see what the value is that we get. So it's 1 plus 10%, but 1 minus 10%, square root of this minus 1, so it's basically minus 0.5.